Hello everyone, in this video lecture I will be briefing you about chemical fuels, next classification of chemical fuels, calorific value of the fuel and how to determine the calorific value of the fuel using bomb calorimeter. Let me discuss all these aspects in the coming slides. First of all, we will see why energy resources are needed. Energy is essential to life and all living organisms to perform vital functions. It may be plants, animals, microorganisms or human beings. Example, we eat food to get energy. Energy is the most important of all resources and Earth is the storage house of the energy. Energy resources are needed for the creation of better world and modern world runs on energy. It is difficult to imagine life without energy. All development activities in the world are directly or indirectly dependent on energy resources. Energy production and energy utilization indicate a country's progress. The growing or changing lifestyle of the human beings has led to the energy deficiency. The world growing energy needs alongside increasing population led to the continuous use of fossil fuel based energy resources such as coal, crude oil and natural gas, which becomes a problematic by creating several challenges such as depletion of fossil fuel resources, greenhouse emissions and other environmental concerns. Energy sources are classified into two types, namely renewable and non-renewable sources. Non-renewable sources are the sources that cannot be renewed or continuously depleted from the earth crust because of human activities. The examples are fossil fuels, thermal and nuclear power. Renewable sources are the energy sources that can be renewed or reproducible. Example, wind, hydro, solar and geothermal energy resources. So here we will see what is a chemical fuel. A chemical fuel is a combustible substance which on combustion in air or oxygen produces significant amount of heat which can be used economically for domestic and industrial purpose. Fuels are generally made up of hydrocarbons which contain carbon and hydrogen as the main component. So these undergo combustion in air or oxygen where carbon and hydrogen present in the fuel are converted into carbon dioxide and water respectively with the liberation of large amount of heat. So this liberated heat can be utilized for various purposes. So in this slide we can see some common examples of fuel. So wood, cow dung, kerosene, natural gas. So this kind of fuel we all have come across in our daily life. So chemical fuels are broadly classified as solid, liquid and gaseous fuel based on their physical state in which they are used. These are further classified into primary and secondary fuels. Primary fuels are the fuels which are found in nature. Example is wood, crude oil and natural gas. Secondary fuel are the fuel that are derived from primary fuel through physical or chemical process. The process is also known as fractional distillation or refining. Examples are petrol, diesel, kerosene or any other petroleum products. Let me discuss classification of fuel in detail. Fuels can be classified into two types. First, on the basis of their occurrence. Second, on the basis of their physical state. As already discussed, we can classify the fuel on the basis of their occurrence as primary fuel and secondary fuel. So what are primary fuel? Primary fuel are the fuel which are used as such as they occur in nature. That is, they can be used without processing or slight processing. Example for a primary fuel is wood, coal and natural gas. Next, what is secondary fuel? Secondary fuel are the fuel derived from primary fuel by chemical processing. Examples are coke, kerosene and LPG. Next, we can classify the fuel on the basis of their physical state as solid fuel, liquid fuel and gaseous fuel. Example for a solid fuel is wood, coal, peat. So these are nothing but the primary fuel. Example for a solid fuel which is secondary fuel is known as charcoal and coke. So these are the products which are derived from the primary fuel. Next, liquid fuel. Example for a primary liquid fuel is crude oil. So what we can derive from the crude oil is nothing but secondary fuel. Examples are petrol, kerosene and diesel. Next, example for a gaseous primary fuel is natural gas. So what we can derive from the primary gaseous fuel is secondary fuel. So these are nothing but producer gas, CNG, water gas and LPG. So here we will discuss about characteristics of a good fuel. We use fuel for various purposes, but how actually a fuel can be useful for us so that we can use it economically and conveniently. When you talk about good fuel, the first important thing which comes to the mind is its calorific value. So calorific value terminology you might have studied in your basic level. Calorific value indicates the efficiency of the fuel. Calorific value is nothing but the amount of heat liberated when a unit mass or volume of the fuel is burned in air or oxygen. Higher the calorific value, more efficient is the fuel. A good fuel must have high calorific value. So in the below chart we can see the different types of fuel and its calorific value. So cow dung cake is having a least calorific value around 6000 to 8000 kilojoules per kg, whereas hydrogen is having some highest calorific value around 1,50,000 kilojoules per kg. Next important parameter to determine the characteristics of a good fuel is nothing but moderate ignition temperature. So first we will see what is that ignition temperature. Ignition temperature is the minimum temperature to which a fuel is to be heated to start combustion. When we lit the fuel or ignite the fuel to start combustion reaction at a particular temperature, the temperature is also known as ignition temperature. Fuels having low ignition temperature can cause fire hazard during handling, transportation or storage. So it's very risky to handle the fuel which is having low ignition temperature. But if the fuel is having high ignition temperature, so it requires lot of energy to ignite the fuel to start combustion. So moderate ignition temperature is the best way to start combustion of the fuel. The third point is nothing but the low ash content. Ash is leftover product after combustion of fuel, also known as non-combustible substance. Solid fuel having high ash content lowers the calorific value and poses disposal problem. Lower the ash content or no ash content definitely increase the efficiency of the fuel. So for a good fuel, the ash content should be very minimum. The next point is nothing but low moisture content. Any fuel which has high moisture content will find difficulty in igniting that kind of fuel. When we bring wood from the trees, by cutting the trees and trying to ignite the wood, we find difficulty in igniting that kind of wood. Since freshly cutted wood might have high moisture content, because of it, it is difficult to ignite the wood. Examples in villages you might have seen. Wooden pieces or logs are kept for drying in sunlight once they are brought from trees. So drying decreases the moisture content of the wood. The presence of high percentage of moisture in fuel decreases its efficiency and also increases the ignition temperature. So it lowers the calorific value of the fuel, since most of the heat produced is utilized to vaporize the moisture present in the fuel. Hence, lower the moisture content, better is the quality of the fuel. Next important properties of a good fuel is nothing but they should not produce any harmful gases or substances. Gases such as carbon monoxide, oxides of sulfur and hydrocarbons are always toxic to the environment. So whatever the products are formed, they should not be harmful. Carbon monoxide, oxides of sulfur, these are the gases which are greenhouse gases which lead to greenhouse effect and also leads to the increase in temperature of the earth. So next thing is nothing but any fuel should be readily available. That is, it should be abundant in nature and cost should be economical. Next important point is nothing but easy transport and storage. Fuel should have convenient, safe and easy method of storage and transport so that minimum risk of fire hazard is seen. Last important point is nothing but control of combustion. Combustion rate can be easily regulated and burning can be stopped as and when desired is the main logic behind control of combustion. So these are the important properties or characteristics of a good fuel.
Calorific value of the fuel. Calorific value of the fuel is nothing but the amount of heat liberated when a unit mass or volume of the fuel is burned completely in air or oxygen. There are two types of calorific value. One is gross calorific value, GCV, also known as high calorific value. The other one is net calorific value, NCV or low calorific value. Gross calorific value. It is nothing but the amount of heat produced or liberated when a unit mass or volume of the fuel is burned completely in air or oxygen and the products of combustion are cooled to room temperature. GCV is given as the sum of sensible heat plus latent heat of condensation of water. Whenever a fuel is burnt in air or oxygen, heat is liberated and the combustion products are formed. The heat liberated is nothing but the sensible heat. The products of combustion are cooled to room temperature. That is, in gross calorific value, the products of combustion are not allowed to escape. The reaction is generally carried in closed container. So definitely one of the product is vapors of steam. So when you go to cooling, what happens here is nothing but the vapors of steam condense back to give the water. So when it condenses back to give the water, it liberates latent heat of condensation of water. So gross calorific value is nothing but the sum of sensible heat plus latent heat of condensation of water. Next is net calorific value, that is NCV or low calorific value. It is nothing but the amount of heat produced or liberated when a unit mass or volume of the fuel is burned completely in air or oxygen and the products are allowed to escape into the atmosphere. So here in the net calorific value, the products are not cooled to room temperature. They are generally allowed to escape into the atmosphere. So NCV is nothing but GCV minus latent heat of condensation of water. So always NCV is lesser compared to GCV. Since the products are not cooled, they are generally let off into the atmosphere. How to calculate net calorific value? Net calorific value NCV equal to GCV minus latent heat of condensation of water. Latent heat of condensation of water is equal to mass of water formed during combustion into latent heat of steam. So let's take an example for an hydrogen as a fuel which undergoes combustion in presence of oxygen, producing large amount of heat plus water is formed. Since 1 mole of hydrogen liberates 1 mole of water, that is, when we take 2 gram of hydrogen, when it reacts with oxygen, it produces 18 gram of water. That is, the mass of water formed is 9 times the mass of hydrogen in the fuel. Therefore, mass of hydrogen present in the fuel equal to percentage of hydrogen present in the fuel divided by 100, which is equal to 0.01 into percentage of hydrogen present in the fuel. Mass of water formed during combustion equal to 9 into 0.01 into percentage of hydrogen present in the fuel. Therefore, latent heat of condensation of water equal to 0.09 into percentage of hydrogen in the fuel into latent heat of steam. Net calorific value is given as GCV minus percentage of hydrogen in the fuel into 0.09 into latent heat of steam.
Determination of calorific value of a solid or a liquid fuel using bomb calorimeter. In this, I will be discussing about principle, construction and working of bomb calorimeter. First, let us see what is bomb calorimeter. Bomb calorimeter is a constant volume calorimeter used in measuring heat, that is energy of combustion process. Here, volume of bomb calorimeter is fixed and it is used to measure the energy of combustion process. So let me start with the principle of bomb calorimeter. A known mass of the sample, it may be a solid or a liquid fuel, is burnt completely in excess of oxygen inside the bomb calorimeter. The liberated heat is absorbed by the water and the calorimeter. Heat lost by burning the fuel is heat gained by the water and calorimeter. Thus, by knowing the rise in temperature of water, calorific value can be calculated. So this is the basic principle behind the bomb calorimeter. Next is the construction of bomb calorimeter. A bomb calorimeter consists of strong cylindrical stainless steel vessel. Basically it is known as bomb with a capacity of 400 to 500 ml. The stainless steel bomb containing fuel is immersed in well insulated copper calorimeter surrounded by known amount of water. Oxygen is pumped at a pressure of 25 to 30 atmospheric pressure inside the bomb calorimeter through the inlet valve. So the control of oxygen can be done with the help of this kind of arrangement. A known mass of the fuel in form of pellet is taken in a platinum crucible which is placed inside the bomb calorimeter. So this fuel can be ignited with the help of the external wire. Next, the thermometer is also placed inside the bomb calorimeter to note down the initial temperature of the water, and after completion of reaction the final temperature can be noted down with the help of the thermometer. An electrical stirrer which is also fixed inside the bomb calorimeter, which ensures the heat released during the reaction is uniformly distributed throughout the water. An outer jacket is also provided which generally acts as an insulator. You can see the outer jacket here, which generally acts as an insulator to minimize the exchange of heat with the surroundings. So this is regarding the construction of bomb calorimeter. Next, working of bomb calorimeter. A known mass of the fuel, basically it may be a solid or a liquid fuel, is taken inside the bomb calorimeter in the platinum crucible. So this fuel is ignited with the help of the wires, which is used for ignition. Oxygen is pumped at a pressure of 25 to 30 atmospheric pressure inside the bomb calorimeter. Next, the fuel undergoes combustion. Initial temperature is noted down with the help of the thermometer. So fuel undergoes combustion, and ultimately the stirrer is continuously stirred throughout the reaction. So initial temperature was noted and the final temperature also noted after the completion of reaction. The heat liberated is absorbed by the water present in the calorimeter. So ultimately, by knowing the amount of heat absorbed by the water jacket, that is by knowing the rise in temperature, the calorific value of the fuel can be calculated. So this is regarding the principal construction and working of bomb calorimeter.
Observations and calculation part. Mass of the fuel is taken as m kg. Initial temperature of water is nothing but T1 degree Celsius, which is noted down with the help of the Beckmann's thermometer before the start of the reaction. Final temperature of water, which is nothing but T2 degree Celsius, which is noted down once the reaction is completed with the help of the Beckmann's thermometer. Next, the weight of water taken in the calorimeter is W kg. Water equivalent of calorimeter is small w kg. So I'll explain what is that water equivalent of calorimeter. Whenever a fuel is burned inside the calorimeter, the heat is liberated. That heat is absorbed by the water jacket, but some of the heat is absorbed by the parts of the calorimeter. That constitutes the water equivalent of calorimeter, which is constant for a given calorimeter. That can be obtained by burning a fuel of a known calorific value. Rise in temperature of water is nothing but delta T, that is T2 minus T1 degree Celsius. Specific heat of water S, which is given by 4.187 kilojoules per kg per degree Celsius. Latent heat of steam, that is represented by L, which is equal to 2454 kilojoules per kg. The formula to calculate the gross calorific value GCV is given by capital W plus small w into T2 minus T1 into S divided by M, where capital W is nothing but the weight of water taken in the calorimeter, small w is the water equivalent of calorimeter, which is constant for a given calorimeter. T2 minus T1 is nothing but the rise in temperature. S is the specific heat of water. M is nothing but the mass of the fuel which is taken inside the bomb calorimeter. Next, the formula to calculate net calorific value or NCV is given by GCV minus 0.09 into percentage of hydrogen into latent heat of steam. Here we should note that specific heat of water is nothing but the heat required to raise the temperature of 1 kg of water by 1 degree Celsius, which is equal to 4.187 kilojoules per kg per degree Celsius. The SI unit for a solid fuel is joules per kg, whereas the SI unit for gaseous fuel is joules per meter cube.